Um, let's see. Oh shoot, I didn't get this set up. So what we're about to get into, I kind of gave us, I can't remember, I didn't really give us too much of a preview. 9.2 deals with slightly higher level algebraic concepts. Like, for example, there's going to be some solvent equations in here. There's going to be radicals. There's going to be something a little freaky, fractional powers. Do you guys, anybody remember anything about fractional powers? All right, we'll get there. Okay. Give me a moment. What is it? AC. There it is. Okay. Connect to this. Yes. Do it. Oh, shit. 3, 4, 5. Okay. Look at Jeff. Yeah. Okay. So let me, all right. First thing we're going to do is we're going to kind of look at completing our idea of real numbers. So there's a type of number that might have come up before, but we really haven't talked about it much directly. Can you guys remind me, what's the official name of a fraction? This kind of number. I might not have said this very much, but I'm pretty sure I said it at least once. What do you officially call it? Like, what's this? Ratio. So this is a ratio of whole numbers, correct? So what kind of number is that? It's a rational number, yes? So anything that can be written as a fraction is called a rational number because I can write it as a ratio of whole numbers. Okay, like, not very creative, but that's math people. It's a ratio, it's irrational. So this is a type of rational number. Can somebody give me an example of a rational number that's not written as a fraction already? So rational number is any number that can be written as a true fraction. So can somebody give me something that's not a fraction, but it's rational? Percent. Sure. 25%. Why is that rational? Because it can be written as? Fraction. 25 over 100, 11. All right, give me another one that's not a fraction or a percentage. Decimal. So like, what kind of decimal? 0.4. Okay, terminating. Or repeating. Yes? Okay, I like it. You guys all with me? Yeah, that's good. And then of course you've got stuff like 5. Is that rational? Of course, because you can write that over 1. Okay. So every whole number, every integer is also rational because you can put them all over 1. Amazing. So the basic definition of a rational number is anything that can be written as a fraction, as a ratio. It makes beautiful sense because the freaking root word, sure, Jeff. The root word of ratio is a ratio. So, I said something earlier about every repeating or terminating decimal. Does every decimal do one of those two things? No, right? So if I have a decimal that doesn't stop and it doesn't repeat, you guys with me? That is not rational. So that's a whole different classification. Now, this is kind of silly. If it's not rational, it must be, what's the opposite of rational? If you're dealing with somebody that's not being rational, they are being irrational. I love it. Cool. So we have irrational numbers. Can somebody give me an example of an irrational number?
1 over 3.
So again?
1 over 3.
Now, 1 over 3 has to be rational because it is a ratio. Yes. I want a number that is irrational. I cannot write it as a fraction. Huh? Pi. Beautiful. Pi. I don't know if some of you guys might think that's cheating, but pi is a beautiful example. 3.141596, and that's all I have memorized, dear God. I don't want to memorize pi for some weird reason. And it goes forever, and as far as we know, there's no pattern. If there is a pattern, it starts in the 58 billionth place. Holy shit, because we know that sucker all the way out. It's silly. Okay. We have supercomputers dedicated, like, whatever we want to do as a human race. Anybody know any more irrational numbers? So, let's develop some. If you think you have one, let me know.
Well, do imaginary numbers count like I?
Oh, imaginary are completely separate.
Okay.
So what we've got, real quick, I still want to give us some more of these, but what we got is rational plus irrational equals real. Yes? So we got the real numbers, and then part of it is irrational, and part of it is rational. Yes? And then imaginary numbers are over here. Off to the side, freaking us out. Okay, I like it. You guys all with me? Sort of, okay. So basically, any number that can be found on the number line is a real number. So before today, if I only included fractions and whole numbers and integers, so here's my integers, yes? And then I have a fraction like -1/2 or, get out here, like whatever the shit, 2.5, blah, blah, blah. You with me? But then that leaves a lot of gaps. If I plotted every single fraction that exists, there would still be gaps. And those gaps are filled in by the irrational numbers. Yeah? Okay, maybe. Is that okay so far? I mean, obviously the integers leave a lot of gaps. When you fill in fractions, you might think we got everybody, but no, we didn't. We didn't get everybody. Because then we have the irrational. So for example, 0.1111 forever. What about the number that's 0.112111? 2 that is irrational because it's not a repeating thing. It's not the same thing repeating. ... But isn't that in between 0.111 and 0.222? Isn't that in between those two? So if you give me any two rational numbers, I can find an infinite number of irrational numbers between them. Let me stop for a minute. And you all know freaking pi, right? You all know pi. You know this. And you should know that it's irrational. It's a decimal that has no pattern and it doesn't terminate. Has anyone ever heard of, not the letter E, but the number E? Yeah. Like pi is a number, correct? It's a symbol we gave a number, a freaky number that freaked everybody in the universe out because you take any circle, no matter how small or big, and you divide the circumference by the diameter, you always got the same number. That's pi. It freaked entire civilizations out. They thought it came from the gods. Blah, blah, blah. E is kind of like used in population growth and so forth. I don't know if any of you guys have ever used the E, but it's a letter, it's like pi. It's 2.7828, blah, 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 blah. And it's a number that pops out of a few different places, and we gave it a letter because it freaked us out. Same thing with pi. Okay. There's one more category of numbers that you all know that would be irrational numbers. So let me build up there. So let me ask you guys this real quick, just to kind of build up to this. Is everybody with me? So we got rational numbers is everything we've been talking about. We haven't really directly discussed irrational numbers yet. I'm going to do that today. So help me out. All right, let me see. It's going to go a little. We're going to have a little bit of a proof here in a minute. How many factors, if you prime factor 36, could everybody prime factor 36 for me real quick? Okay, so if you prime factor 36, you could have done this several different ways, yes? In fact, wouldn't every square number have an even number of prime factors? Do you guys see what I mean? Because it would always break up into half of something, yes? 36 breaks up into 6, 6, and those break up into 2, 3, 2, 3. You with me? Any square number would do the same thing. Are you guys with? Let's do one more example. Not 9 is silly, but 9 would be 3 times 3. 64 would be 8 times 8, which would be 2 times 2 times 2 times 2 times 2 times 2. There's an even number of factors, yes, of prime factors. Are you guys with me? Okay, I like it. I really want you guys with me. This gets a little tricky. Do you all agree? And does anyone remember what I called this? Probably not. You're like, I don't listen to you, man. What am I supposed to do? I call, when you prime factor something, I'll call that the DNA of the number, because when you put those together, you can only get 64 back. When I put this together, I can only get 36 back. Yes? It's kind of silly. If I had one number that had an even number of prime factors and another number that had an odd number of prime factors, could those two numbers equal each other? If I had one that has an even number of prime factors and another number that had an odd number of prime factors, could those be the same number? No, there's no way a number can have both an even number of prime factors and an odd number of prime factors. So you guys kind of with me. I love you guys. You're all like, shit, just get to where you're going. Is everybody with me so far? So, here's the primary problem. If I wanted to solve x plus 3 equals 0, what kind of number do I need to solve that? What kind of number do I have to use? Negative numbers. So we have to invent negative numbers. Yes? If I want to solve 2x plus 3 equals 0. Is everybody with me? Because the answer here would be negative 3. Yes, the first one. What about 2x plus 3 equals 0? What kind of number do I need to invent so that I have an answer to 2x plus 3 equals 0? Fractions. Yes, you guys with me? So as a human species, we started with 1, 2, 3, because that's what we could freaking see. And then we had when we got more advanced kind of problems we had to solve, we had to create new kinds of numbers. Or there's an argument about if we discovered them or if we created them. I don't care. So you guys come. Okay. So what about this equation? All right, here's where it's going to get a little trippy. If I assume the answer to this is rational, what does it mean x would look like? If it's rational, what does it have to look like? A fraction. Good. I want you guys with me. Can you tell me the most give me like a general fraction. What could give me? I don't know what the answer is, but it's got to look like a fraction. So I can say x is like a over b. Is that cool? Okay. So I'm going to assume that this equation has a rational answer, which means it has to be able to be written as like a over b, where a and b are whole numbers or integers. Okay, I love it. So that means that a over b squared must be 2. Which means that a squared divided by b squared must be 2. Which means that if I multiply both sides by b squared, I get a squared equals 2b squared. Now, a squared is obviously a squared. A is a whole number. That's because it came from a fraction. Are you guys with me? If a over b is rational, a must be an integer. So a squared is a square. It's like 36. What did we say? How many factors does a squared have? Since it's a square number. What is true about the number of factors? It's got to be an even number. I love it. What's true about b squared then? Even number. But then when I multiply it by 2, how many total factors are on this side? If b squared has an even number, and then I put a 2 next to it, how many factors does 2b squared have? So, could b squared have 6 prime factors? Some even number. 2 times that means now it has 7, yes? So one side has an even number of prime factors, and the other side has an odd number of prime factors. Could a squared ever equal 2b squared if a and b are both rational? Are both integers. So much. So, if I assume that this equation has a rational answer, That means I can write it as A over B, yes? If I plug that in, that leads me to this statement. In order for my assumption that it's rational, in order for that to make sense, this statement has to make sense. But it doesn't, because one side would have an even number of factors and the other side would have an odd number of factors. So that is kind of like what's called a proof by contradiction. If I start with an assumption and that leads to a contradiction, my assumption is proven wrong. So my assumption was this equation had a rational answer. So this equation, since that's wrong, it must have an irrational answer. Does anyone know, of course, what the answer to that is, or what one of the answers is? Square root of 2. The other answer is negative square root of 2. So up here, in our list of irrational numbers, what can I put next to this? Square root of 2. Any square root I can't do. Square root of 3, irrational. Square root of 4, not irrational because it's freaking 2. You guys with me? Square root of 5 is irrational because it can't do it. Okay. So, we have developed now an idea of what an irrational number could be. Besides pi, besides e, we also have the radical stuff, the square roots. Okay. And is anybody, you guys have done square root stuff before? I think it's come up in this class before. Real quick, help me out. What's the square root of 9? 3. But what's the answer to x squared equals 9? Or? Good. So when you see this symbol, when you see square root of 9, that is understood to be the positive root. Because how many roots does any positive number have? 2. One's negative, one's positive. How many square roots, I should say. So when you see the symbol, the square root, they've already chosen the positive one. So that's why this is just 3, but this equation has 2 answers. 3 and negative 3. I love it. So it's something called the principal root. Principal square root. Stop for a minute. Okay. Let me ask you this. I can't remember if this has come up before, but if I just write this name down, what does this relate to, this person? Yeah, what about a triangle? What kind of triangle? I got you. I'm with you on this, on the sign language. Right angle, right triangle. Yes? Does anyone remember what good old Pythagoras? It was actually his followers that did all the work, but he took all the credit. That happened a lot in mathematics. What did this old Greek dude say? Yeah, a squared plus b squared equals c squared. Like, so if I wanted to construct something that has a length of square root of 2, I could do it on this grid paper. We zoom in a little bit. So if I made a triangle that had, this is 1 and this is 1, correct? Automatically, what must this be then? Well, let's solve it. It's definitely a right angle there because I'm using, even though my poor little box looks a little smushed. What would Pythagoras say about this? I don't know C, correct? So how would I figure it out? What would I do?
1 squared plus 1 squared.
Yeah, c squared is 1 squared plus 1 squared. C squared is 2, yes? So C, now why am I picking the positive? Because it's a freaking physical triangle I'm drawing. It's not going to have a negative, yes? So if you draw, and of course I didn't do this perfectly, but if you drew 1, 1, and they were at right angles to each other, when you connect them, you've drawn something that is exactly square root of 2 long. Are you guys with me? Without needing a ruler. I've drawn something that's exactly square root of 2 long. If I did that perfectly. I don't know if you guys are really with me. No? Screw you, Jeff? Okay. That's kind of nifty if you think about it. I mean, on a grid paper, I could draw 1, I could draw 1, And then if I do this, that's square root of 2. It has to be the square root of 2. Okay. Alright, enough of that. Okay. So, if I wanted to figure out, for example, where the square root of 2 fits on a number line, I could kind of do this. If I consider this falling down, it would fit about right there. You guys see that? If I just kind of push that line down, that's about where the square root of 2 is. Now, of course, nowadays we know what the square root of 2 is. If you put it in your calculator, it's 1.414 blah, 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 forever. Yes? Okay. So, more directly, if I say 10 divided by 2, that's the number that it takes 2 of to add to be 10. Now, I know we all know it's 5, but just what does 10 divided by 2 by itself mean? It is the number that it takes 2 of to add to be 10. That's one way to look at this, yes? So what does the square root of 9 mean? It's the number that it takes 2 of to multiply to be 9, yes? Okay, I love it. Kick ass. Kick ass. So if I wanted you to do something like, you got it, Jeff. Square root of 729. How could you start to figure out what that might be? Or even if it's doable. If the square root symbol means what does it take 2 of to multiply to be the thing inside, what can you start doing to 729 to start investigating it? What number do you know goes into 729? Even higher. What's 7 plus 2 plus 9? 7 plus 2 plus 9. 18. And 18 is a multiple of 9, so what goes into 729? 9. So this is 9 times 9 goes into 72. 8, 9 goes into 9 once. Yes? Okay. You guys kind of with me so far? So this is 9 times 9 times 9. Yes? Which has got 3 9s, not just 2. You see the problem? But this is 3 times 3 times 3 times 3 times 3 times 3, yes? So let me ask you, is everybody kind of with me? So this is the idea of, I know the idea of a square root. So if this person gives me this big ass number, what am I going to do? I'm going to start breaking it down, because that's the whole point of a square root is, what does it take so many of to make this number? So let me break the thing down, see what it's made of, yes? Can you guys see 2 groups of something down there at the bottom? What do you see 2 groups of? 2 groups of how many 3s? So it's 2 groups of what number? 3 times 3 times 3. 27. So what's the square root of 729? 27, because it takes 2 27s to multiply to 729. Are you guys kind of with me? Okay, I like this. I like the fact that some of you guys kind of like woke up a little bit. You're like, oh, I like this guy. Oh, well, that's kind of interesting. Okay. That is kind of cool. So that is an example of something I could give you on a test. And I just want to start dividing it. And this is where divisibility rules kick so much ass. Use the divisibility rules to figure out what to divide the thing by. Yes? Okay. So. Okay. Oh. What kind of calculators do you guys have? Out of curiosity, how many of you guys have a TI calculator? You have a TI calculator. A TI graphic calculator, I should say, sorry. Do most of you guys have like this kind of calculator?
Yeah.
Okay. Turn off, okay. So do you guys, if you have this kind of calculator, can you see where your square root button is? Yeah, so not surprisingly, it's right above the square button on this calculator. Now on your calculator, it should be, normally they're right, they kind of like to put Square root is sort of an inverse of a square. I say sort of because it really isn't technically, because it can't give you a negative answer, but it's close enough. A square root would undo a square. Yes? So they like to put those kind of things together. On this specific calculator, can I do a cube root of something? And in fact, we still have to talk about what the shit a cube root is, but do you see right above the square root button?
Yeah.
What's above the button that's above that? So there's a square root button. What's above the button that's above that is the xth root. Yeah. So if I did, so real quick, what's the square root of 9 again? Why? Because it takes 2 3s to multiply 9. What's the understood number in the square root? We just don't write it, but we call it a square root. What's an understood number there? 2. So what would the cube root of 8 be? What would that ask you to do? So cube root of 8. What number does it take? If the square root is what number does it take 2 of to multiply this, the cube root is what number does it take 3 of. So what number does it take 3 of to multiply the 8? 2. So if I do the cube root, so I hit the 3, hit the root button, and then put 8. There you go. Cube root of it. Sweet. So, depending on which kind of calculator you have, you should definitely have the square root button showing up. If you don't have this button showing up, I will show you how to still do that anyway. We'll come back to that in a minute. So you should definitely have a square root button. You might not have the x root button. I don't know. You have to show me. All right. So with real numbers, we kind of inherit all the properties. We have commutative property, associative property, all the properties we've been talking about this whole semester. They work with real numbers. So real quick, what does that mean? If I had to do the square root of 7 plus the square root of 11 minus the square root of 7, what could I do? Yeah, I could use associativity, commutativity to put these things together, and then my answer is square root of 11 because these guys kill each other, yes? Now very quickly, what is the square root of 3 plus the square root of 5? Is it the square root of 8? Oh, hell no. Yes? Because what do you need in order to be able to add things? You have to have like terms to be able to add things. So if I have 3 plus 5, why can I add those? Because I have 3 1s and 5 1s, so I have 8 1s. This is half of 3 plus half of 5. I don't know what the shit that is. So I can't add those together. But what's the square root of 3 plus the square root of 3? 3. What's x plus x? So what's the square root of 3 plus the square root of 3? 2 square root of 3. Yeah. So let me ask you this. All right, let me ask you this. What does the square root of 3 represent? It's the number that it takes. Well, you know, it's weird. I don't know what this number is, but what does it represent? It's the number that it takes 2 of to multiply to be 3. So what is the square root of 3 times the square root of 3? Square root of 3 means the number that it takes 2 of to multiply to be 3. So when I multiply 2 of them, I should get, just said the answer, yes? 3, good. So half of 3 times another half of 3 is a whole 3. Okay. I like it. Okay. Yeah, okay. We don't have to do all that. So let's look at this. If I wanted you to figure out what the 5th root of 32 is. What is that asking you to do?
What number does it take 5 of to get 32?
Yeah, what number does it take 5 of to multiply to 32? So of course, what would you do?
Break it down.
Break it down. Yes. And now you gotta guess the answer, because I mean, it's only one number that goes into 32. Well, do you understand what I mean? 4 goes in, but 2 goes into 4. 8 goes in, but 2 goes into 8. So the only thing that really goes, that makes 32 is 2's, yes? Because that's 4 times 8. That's 2 times 2 times 2 times 2 times 2, blah, blah, blah. So of course this answer is 2. Yes, so it takes 5 2's to make 32. So there's another way to look at a root. So before I forget real quick, just to look at the definitions of some of the stuff. This number inside is called the radicand. This number here is called the index of the root. This symbol is obviously a root, but it's also called a radical. Sometimes they call them roots, just because. Okay, so here's where things get trippy. If I ask you what is the square root of 25, you should say, oh, thank God, because what is the square root of 25? So, what does the square root do to a number? It's a weird question, but let me just say this. Doesn't it cut it in half somehow? Okay, so if I ask you to cut 9 in half additively, what that means is, what number do I add to itself to make 9? So that's what we consider. When I say cut 9 in half, you would say 4 and a half, yes? If I said cut 9 in half multiplicatively, that means what does it take to multiply to be 9, yes? So this is still an idea of cutting it in half. I'm just cutting it in half with respect to multiplication instead of addition. What does a power mean?
Doubling in respect to
Say again?
multiplying by 2.
Yeah. Well, multiplying that number twice, yes? Multiply. So the 2 means how many repeated multiplications I want. So it's based on multiplication, yes? So I'm not sure how many of you guys have ever seen this. But another way to write a radical, square root specifically, is as a 1/2 power. Because what does the square root of 25 really mean? It wants me to cut 25 in half multiplicatively. I really want this to make nothing but sense. What is 4x? Tell me what 4x means without using the idea of multiplication. Yeah, I want 4x's adding, correct? So if I want to cut x in half additively, I would put 1/2 in the spot. That means how many times I'm adding it. A coefficient is the number of times I'm adding the thing it's in front of. 4x means add the x 4 times. So if I want to have half of an x additively, I would just put a 1/2 in the spot. That means how many of them I'm adding, correct? If I want to do half of something multiplicatively, I'm going to put a 1/2 in the spot that means multiplication. And that's an exponent. How many things I'm multiplying? Maybe. So let's see. Watch this. Can you write 25 is definitely 5 squared? You all agree with me? Also, what is x squared cubed? What do you do with those powers? You multiply. 11. Now somehow I'm going to combine these two ideas together. So the square root of 25 is the square root of 5 squared. Is 5 squared to the 1/2 power. Okay, let me stop for a minute. 25 is 5 squared, that's a fact. So all I did from the first step is I'll replace 25 with 5 squared. The square root, my claim is, I can write that as a 1/2 power. Now if all this shit is true, whatever answer I get better be freaking 5, because that's what the square root of 25 is. What do I do with these powers? Multiplying. What's 2 times 1/2? Freaking 1. Okay. So a square root can be written as a 1/2 power. A cube root can be written as a 1/3 power, so forth, yes? So let's investigate. Well, here, real quick, can you guys do this? What's 27 to the 1/3 power? It's trying to be a 3. Poor little dude.
9.
No. That would be 27 times a third. It would be 3. So you can do this 2 ways. Either think of it as the cube root of 27, and what does it take 3 of to multiply to be 27? Right, 9 times 9 times 9 is way too big. 3 times 3 times 3, exactly right. Or, 27 is 3 cubed, those cancel, and I get 3. Okay, maybe. So you have to be really careful. Fractional powers, radicals, they must mean something different. They can't mean division. They have to mean something different. And since they both involve multiplication, I've got to think backwards about what does it take, how many up to multiply to be this thing. So, how about this? What would this be? X to the 2/3 power. So let me see. Can I rewrite this as x to the 1/3? What would I put on the outside to make this the same thing? What would I put out here?
3.
No, because then 1/3 times 3 would be 1. I need it to be 2/3, yes? I want this equality to be true. What do I multiply 1/3 by to get 2/3? 2. What is x to the 1/3? How can I rewrite that? Cube root. I could look at this a different way. What if I put the square on the inside and the 1/3 on the outside? Then this would be the cube root of x squared. So it doesn't matter where the power goes. So real quick, most plants, where are my botanists? One semester I said this and somebody said, well, technically, Jeff, most plants have roots where? On the freaking bottom, yes. One semester somebody in the back was like, actually tubers, no, I'm quiet. And I can do that because I'm a nerd, so I can point out fellow nerds. So when you see a fractional power, the bottom is the root, because that's where roots are in plants, and the top is the power. This is powerful, so the top. So if I had to do something like 8 to the 4/3, can you interpret that power for me? What's the root? 3rd root, yes? Cube root of 8, and what's the power? 4th power, yes? So the root's on the bottom, power's on the top. And what's the cube root of 8? 2. And what's 2 to the 4th? 2 to the 4th? 16. Sorry, I almost fell asleep. There's another way to look at this. Is really cool. So you guys agree? This wants 4/3 of 8. This wants 4/3 of 8. Can you break 8 up into thirds? What do you get when you break 8 up into thirds? Break 8 up into 3 parts. 2 times 2 times 2, yes? You with me? 2 times 2 times 2. And it wants 4 of those. 4/3 would be 4 2s. So this would be 1/3 would be 2. 2/3 would be 2 times 2. 3/3 would be 2 times 2 times 2. 4/3 would be 2 times 2 times 2 times 2, which is frickin' 16. Shit, yeah. So there's another way to look at a fractional power. It's just that much of this number after you break it up into the right number of parts. Now some of you guys are kind of sitting out there going, God damn, this guy brought fractions back. How the shit did he do that? But we're not going to do like a crazy amount with these fractions. Okay. Here, you guys try this. Let's see if you remember what this means. What do I want? Okay. 64 to the negative 2/3. All right, so how did anybody do this? What part of this did I bring back that I haven't talked about in a while? The negative power. What does the negative power mean? Flip it, yeah. Flip what though? That's what you gotta be careful about. Do you make it 3/2? Is the 2/3 being raised to a -1 power? What's being raised to a negative power? 64 is being raised to a negative power. So I'm going to make this 1/64 to the 2/3. So everything's going to happen on the bottom now. How do I interpret that power? What two things does that power want me to do? It wants me to cube root. And it wants me to square. Say we know the cube root of 64 off the top of your head. If you're gonna take a guess, what would you guess?
Less than 8.
I love it. Less than 8 is correct. Because the square root of 64 is 8. So start breaking the thing up. Cube root of 64 is 8 times 8, which is 2 times 4 times 2 times 4. Do you see this though? Isn't that 4 times 4 times 4? Alright, so that's 4. There's 16. So it's not bad to know some of your cubes. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. So I always think it's kind of neat that that we're next to the intersection of 2 cubed and 5 cubed, right? The 8 and the 125. Only a math person would do that. I'm sorry. Okay. So let me ask you this then. Let me push my luck a bit. Let's see. Yeah. Okay. How you guys feeling about that? So if I just give you a number to a fractional power, the bottom's the root, the top is the power. Okay. What about this? Okay. Everybody try to do this problem. Ready? Let me start you off nice. Just make sure we remember how everything works. What's x squared times x to the 5th? Anybody? Yes. X to the 7. Oh, so you add powers when you have like bases. So here's what I can kind of do to you. So what about x to the 2/3 times x to the 1/4? So if you had a student that told you the answer was this, is that correct? What did they get right in a wrong way? They added, so they got that right. So you say, okay, good. You're supposed to add the powers when you have like bases. Unfortunately, your powers are fractions, and of course you need common number. So, what's the right way to do this?
2/3 is 1/4, that should be like.
Yeah, so you're gonna multiply this by 4, you're gonna multiply this by 3, so I get 8/12 plus 3/12, and that would be 11/12. So, be really careful. Now that we know roots are fractional powers, and we know how powers work with like bases, I can combine those things. So I'm really sorry if you're like, oh good, we're outside of the fraction section. You're never outside the fraction section. You can always come back. So of course, what about this here? Yeah, we do. Oh, it's trying to be a 5. Should be a 5. So I made this one a little bit better. Right? Because it's a little bit easier to get what you need. Yes? What is it you need exactly? I need another break, Jeff. 1 week wasn't enough. What do you have to make the top become? And now you can do it. What's 6/10? What do I do with those? Subtract, of course. So what's 6/10 minus 7/10? Negative 1/10, and you can make that 1/8 to the 1/10 if you want to, either one of those. It's kind of convention to not end with a negative power, so we normally flip any negative powers, but either way. So all the same old properties of power still holds, even though the powers now can be fractions. The same power property. Okay. What about 4th root of x to the 8th? Can you rewrite that in fractional powers? Careful. What goes on the bottom? Because it's the bottom of plants. Roots go on the bottom. Powers go on the top. So this will be squared. Yeah. So you can see a shortcut. You just go 4 into 8, right? And then finally, what about this here? Cube root of x to the 12/7. A certain way I would do that would make it look a little bit better. How do I write, real quick, how would I rewrite the cube root of m? I would write that as m to the 1/3. So I got stuff cube rooted, yes? So I'd write stuff to the 1/3. And then what do I do with those powers? No. Multiply them. And when I multiply fractions, what do I kind of look for diagonally? I want to see if anything cancels. So 3 goes into 12 4 times. So I get x to the 4/7. If you'll notice, 4 goes into 8 twice, 3 goes into 12 4 times, over 7, yes? So the shortcut would still apply. Maybe. Okay. we'll talk a little bit about solving equations, and then I've got a little handout that I want you guys to work on. Yeah, good, we don't have too much time. It's a lot of me talking, I'm sorry, it's just the way it works sometimes. Help me out, okay. An equation versus an inequality. Can somebody give me an example of an equation? Give me an example of the equation. That is an expression that needs to be simplified. I want an equation. What does it take for something to be an equation? What does it have to have E in it? Equal something.
So 1 plus 2 equals 3.
Do it again.
1 plus 2 equals 3.
Okay, so in a sense, that's an equation. It's more a statement of equality, but it is sort of an equation. To make this more like our traditional algebraic equation, I could put instead x plus 2 equals 3. So you're right though, 1 plus 2 equals 3 is the type of equation, it's more of a statement of equality. X plus 2 equals 3 is our traditional equation that we have to solve, yeah? Now, what would be an inequality? I'll start us off. 2 is less than 3. Now, can you give me something that's got variables in it? That would be an inequality.
2x is
2x is
less than 1.
less than
Y.
y. Okay, sure. Yeah, let's overload this sucker with letters. I love it. So you've got an idea of solving equations, and you've got an idea of solving inequalities. They are very similar to each other. Now, obviously, that equation they give us, how would I solve this?
Subtract 2 from both sides.
Yes, subtract 2 from both sides. Okay. How could you show this to students in a more physical way? There's a very classical way to do this, and I don't blame you if you're not sure. But is there a physical kind of way to show this to a student? I would accept. Do you remember how we did addition problems in the first place? Visually. What did we do? Circles. I love it. With stuff inside, yeah. So I could do, I don't know, plus 2 equals 3, yes? And then I could either say it's like a missing addend, and go, okay, it's gotta be the 1. Or I could actually take 2 away from both sides, and then I end up with question mark equals 1, yes? Yeah, I like it. You've also got something that it's okay to show students when they're younger, but it gets really, really old really quickly, is this idea of a scale. When you have an equation, yes, you talk about the balance of an equation. So, for example, it doesn't matter, Jeff. If I have like x plus 2 equals 4, so I have this little scale. Unknown box containing coins, and then 2 coins equals 4 coins, yes? So what do I do physically? You can actually have a scale set up and do this. What would I do physically? To maintain balance, what could I do? I could add more circles, but what would get me closer to knowing the answer? I could remove circles. How many circles would I remove? That's insane. So if I remove 2 circles, I figure out the box is 2. And that's equivalent to what you guys know when you would do. You would freaking just subtract 2. Of course you would subtract 2. But you're talking to little people that aren't used to freaking equations. You want to start with something physical that they could put their hands on, or they could draw at the very least, yes? So you guys, I'm certain in your algebraic career, you've had people talk about the balance of an equation and so forth. It gets really, really old. But when you're first learning this stuff, you can have an actual scale that students can put stuff on. Oh, what about this? Here. Let me see what you guys think. What part of this picture was my X? The box. What's in the box? So, can you guys try to draw this equation the same way I just did with the scale? It doesn't matter, Jeff, yeah. Let's just do, sure. Try to draw that directly using a scale picture like I just did. Oh, yeah, good. So just to give you a little help, you're not sure, every X is a little box. So how many boxes you're gonna end up with on that side? That's crazy. So we got 3 little unknown boxes, plus 1. Oh my God, somebody sat on that box. Get out of there, poor little dude. Plus 1 coin equals 4 coins. So what's the very first thing you can do? Yeah, take a coin away. Now this is obviously very, 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 very simple. You want to start with some stuff that's a little on the simple side before you build into just purely mathematical. Where would you go from here? What would you do? Besides redraw this, because it's driving me crazy. What would you do? What does that mean, divide by 3? What does it mean physically? I want to physically be able to do this. If I had a scale in front of me. Going way back to chapter 2, I think it was, where we talked about a one-to-one correspondence. What must a box equal then? Coin. So therefore box is 1. Which means, going back to my equation, X is 1. Now if you wanted to divide by 3, you could do that, 3 groups, divide by 3 means take 2 groups away from each, and then you end up with box equals 1 the same kind of way. Now obviously this kind of breaks down a little bit when you introduce the idea that the answer could be fractions, but you start to move towards a purely mathematical way of doing this. Okay. So what's the only difference between, so real quick, before I go too far, how would you solve this equation? Can you guys do this? Yeah. How would you solve this equation? Not within a scale, just directly, just pure math. What was it from algebra that your algebra teacher said a billion times? Get all the X's and ones, numbers, yeah. The last thing you almost always did was divide, right? You don't divide too early because then you make fractions when you don't need to. So screw that. So what's the first thing somebody did? Subtract. Oh, add 1. Okay, add 1. Subtract 2x. Divide by 2 is crazy. So when I teach like a pre-algebra class or something, I try to tell students what you're trying to do is unbury the x. The x has been buried under all this stuff. Right, so if you get lucky enough to teach not lucky, I don't know, it depends on what you want to teach. If you end up teaching a high enough grade that they're learning algebra, something that's not a bad idea to do is to say, give me a number. 3, that's crazy. Right, so I'm gonna say x is 3. If I double that, what do I get? That's insane. If I subtract 1 from that, I get 5. So this equation that we just created, we already know what the answer is. how do I solve it? I start undoing all the shit I did to the poor x in the first place. I start to unbury my poor x. I buried it under doubling and subtracting 1, so I'm going to add 1 and cut it in half. Kind of unbury it, yes? So it's not a bad way to kind of approach. What you want to inform students though, in fact, you guys know this, we just created an equation where I just started with the answer and it has no application to the real world immediately. That doesn't mean shit right now for the real world. Could that equation mean something in the real world? Hell yes. So in the sterile environment of the classroom, I could create an equation that has any answer that I want it to have. In the real world, from observations we make, we get equations that we then want to know how to solve. So you always kind of want to tell students, especially when they're a little bit older, what we're doing in the classroom is learning the ideas that you will use in the real world, depending on what field you go into. So very often, equations in the real world come from observations we make, and then I have to know how to solve them, so we need to have these contrived equations to get used to the process of how to solve them. Okay. So, does anyone remember the main difference between solving equations and solving inequalities? There's one little thing that gets weird. And let me just start with the heart of it. What would you do to solve negative x is greater than 4? Why is that not solved? Is x by itself? No. So what would you do to get x by itself? Yeah, and of course I didn't say this, because I know you all know this. Whatever you do to one side, you have to do the other side and maintain the balance, which is why the balance is actually a pretty good thing to do in the first place, but not with students who are a little older who've seen it a billion times, like enough for the freaking balance. So if I divide both sides by -1, is this right? That is incorrect. Does anyone know why that's incorrect? Because you're a math person and math people are mean and they just make things wrong. No. What has to happen? You have to flip the sign. Does anyone know? Does that sound familiar to anybody? Does it sound familiar? You have to flip the inequality symbol. Why? Why?
Because you're transferring over the negative sign, so it has to like flip so that the positive number is bigger than the negative number.
Good. So if we have an example like which one of these is bigger?
1.
That's crazy. If I divide both sides by -1 or multiply by -1, right? If I divide or multiply by a negative, I'm gonna get 2 and -1. Which one's bigger now?
2.
Holy shit! There you go. Why do you flip it? Because I can move that. Not very often can I just go because, but that's because that's the way the numbers work. When I multiply, let me see if you guys are cool with this. You remember when multiplied by negative, we figured out that it's rotating? So multiplying by a negative, whatever was on this side is now on that side, and whatever was on that side is now on this side. It's going to switch which one's bigger and which one's smaller. Here's another way to look at this, just in case that wasn't boring enough. I want to show you. This is kind of cool, and I know we don't all agree with me, but real quick, I would never do this if I were you. I would never do it this way. But watch. Couldn't I add x to both sides? And then I could subtract 4, yes? What does that say? The answer?
Negatives are bigger than x.
What does that mean about x? If you read it the other way. So, you can think of this process, you can think of this as being a shortcut. Instead of doing all this shit and bringing the x to the other side of the inequality symbol, I just flip the inequality symbol instead. You guys kind of with me? Instead of doing all this shit, never do this. I could just do the shortcut, which is switch the symbol. Instead of taking the variable to the other side, just switch the symbol. Okay, I love it. So solving inequalities is exactly like solving equations. Everything's the same, except if you multiply or divide by negative, you gotta switch the symbol. I love it. So anytime you're about to teach some idea to your students, you want to really make certain that you understand why every step happens, because somebody's going to ask. And if they don't ask, you get worried. You're like, guys, this doesn't make obvious sense. So let me, show you why this works. Last little thing. So if I had this equation, blah, 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 2x plus 5 is greater than 3x minus 1, this inequality. Let me just kind of do this. So I'm going to subtract 3x just to be that way. I'm going to subtract 5. And then I'm going to divide by -1. So that means it becomes this, yes? How do I graph that? How do I graph that on a number line?
Well, it's a line and then it's a dot.
Do 0, let's put 6.
There's like one dot that's like filled and one that's not.
I got you.
I can't remember.
So, real quick, isn't there shading involved?
Yeah.
And where am I going to shade? I'm going to shade on the numbers that do what? That work. Yes? I'm going to shade the numbers that work. Does that make sense? So what you're concerned about right now is what the hell symbol do I put on the 6? So let's think about this. If I'm going to shade all the numbers that work, does 6 itself work? Is 6 less than 6? So if I'm going to shade all the numbers that work, am I going to shade 6? No, so I'm going to put an open circle. Now something you're really going to love is, we don't use open circles anymore. We're past that shit. We're going to put a parenthesis. You guys remember that? No?
No, I remember the circles.
I love
That's what
you.
you can explain.
Alright, so let's just stick with the circle for now. Have you guys ever done interval notation? Like that?
Yeah.
Some of you guys have, some of you guys haven't. Okay, there. It's fine. So then I would shade this way, yes? How can I check my answer?
Plug it in.
Yeah, I could take, now real quick, I'm not gonna, what would I plug in?
Anything but 6. Well, everything shaded.
Yeah, so if I pick a number here like 0, where am I gonna plug that into?
Both sides.
Where? Not here, because I could have made a mistake to get there. I'm gonna plug it in up here, yes? What do I get when I plug a 0 in? What do I get on this side? When I plug a 0 in for x, what do I get? If I make x 0, I get 5. And what do I get if I make x 0 on this side? -1. Is that a true statement? Yes. What if I pick something over here? Give me a number that's over there. That's crazy. So what do I get when I plug an 8 in here? 16 plus 5 is 21. Is that greater than 8 times 3, 24 minus 1? Is that true? No, good, because I said it shouldn't be true, didn't I? So if you pick a number where it's shaded, it should work, and if you pick a number where it isn't shaded, it should not work. So there's still a way to check, even though there's an infinite number of answers, correct? I can still check. Okay, maybe. I love you guys. What should happen if I plug a 6 in? Be more specific. It shouldn't work in what way? These should end up being equal to each other, yes? 2 times 6 is 12 plus 5 is 17. 3 times 6 is 18 minus 1 is 17. 17 and 17. Okay. So, let me give you this. Let me finally shut the hell up. So what I want you to do, let me give this to you first, and then I'll figure out how much I want you to do. Let's see. Okay, I'm gonna give you guys a bit of a challenge, but I mean, so this is an example of a worksheet I gave to my Math 80 students back in the day when I could teach that, or even Math 90. I would give them this worksheet, right? And see how I start with x equals 3, and then I kind of build on it, and I do it a few different ways, just to show them that idea I showed you earlier. that one way to look at equations is some jackass put some shit on a poor little number, and I'm trying to save the number. I got you, I hear you. Yeah. So I'm trying to unbury this thing, yes? It's not a bad idea to talk about, and again, you can talk about the real world's not like that, blah, 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 but right now we're just trying to get the idea. A few examples of how to do it directly, and then, of course, these shouldn't be too hard, yes? So we're going to do these together really quickly, and then I'm going to let you work on the ones in the back. And look at that one. Yeah, okay, that one won't be too hard. How do I solve this first dude? Do it again.
You add 11 on both sides.
Yeah, so you're always trying to get the x by itself. And really what you're first trying to do is get all your x's kind of like on one side, but they're already on one side together. So then you're thinking, who's in the wrong place? I know I'm over-analyzing this, but just, you always bear with me, so just do it. Then you think, okay, the 11's in the wrong place, because I want this side to just be x's. Whatever, and what I always get is somebody does something like, this isn't really a good place for this, but somebody does something like this. How is that immediately wrong? How can you tell it's immediately wrong? Because the 11s won't cancel. The whole point is I want it to cancel. So you got to make sure that what the hell you're doing will actually cancel what you need to cancel. So what do you end up with? That's insane. So if I want to check it, I just plug it back in. 20 minus 11 is 9. Ooh, okay. 2, this is a really good place for this. You ready? How does that look? Good. Some of you guys are like, this guy's what they give me. So that's obviously a mistake. This is a very, very, very common mistake. It's a mistake I can understand. It's a mistake that's not as bad as a mistake could be. They know they want to kill the 3. What do they not consider though? What operation is currently happening? So of course I have to use the opposite operation. So the only way you can cancel something is by applying the opposite operation. So of course, what operation do I have to apply? Freaking division. So you end up with negative 4. That's crazy. So then if you check it, 3 times negative 4 is negative 12. Sweet. What about number 3? There's another mistake that happens here. Can somebody tease out the mistake that might happen here? I said, if you want something to cancel, you do the opposite operation. What operation do you guys see on the left side? Addition. So somebody would subtract 8. But that's not right, because what is being added? So I have to subtract negative 8. What is minus negative 8? Plus 8. Now, of course, I think most of you guys were going to add 8 to the damn thing, because you're like, it's negative 8. How do I make it 0? I freaking add 8, right? But you understand the very basic mistake a student can make and they think they're following your instructions. I'm adding negative 8, so I have to subtract negative 8, which is minus negative 8 is plus 8. I have to add 8 to both sides. Okay. Plus 8, plus 8. And what do I get? Negative. And then, of course, here you get all kinds of mistakes. Can somebody tell me very quickly if a student put negative 19 or they put whatever, what's one thing you would say to them besides, well, that's wrong? If I put like negative 19, what would you tell them? I'm your student. And I put negative 19, because that's 11 in it, leave me alone. What's one way you could explain to me that's wrong? So anybody tell me, how could you tell me very quickly that negative 1 plus 8 cannot be negative 19?
You're adding 2 opposites, so you can't.
Okay, you can go back to the thing about if I've got different signs I'm supposed to subtract. It's not a bad idea. What physical example could you give me? If I'm a little older student, I'm carrying a wallet. So I understand stuff that goes into wallets. What would negative 11 mean? Yeah?
If you're giving your friend $11, but you only have 8 in your wallet, how many dollars do you still need to give them?
Oh, okay. So if I owe my friend $11 and I have $8 and I pay them as much as I can, I still owe them. Yeah. And for older students that understand money, that's beautiful. Because the minute you understand money, you're dealing with money all the time. Right? Even when you're young, you're like, I know exactly how much money it takes to get a freaking midnight Milky Way and a slushie at the freaking convenience store. Right? That was my go-to. Take our bikes and ride down. I lived the 80s. I didn't just watch them. Sorry. So yeah, okay, so be prepared. Again, solving equations is a fantastic place to celebrate the attempt at correct logic, right? There are some situations on there where the logic was good, it was just they didn't apply it directly. So you don't want to just make a student feel like, no, it's completely wrong. What the shit's wrong with you? You want to show them what they did wrong, but also say you were thinking right in this way. So of course, what am I going to do here? Yeah, what would you say to a student who didn't know what to do here?
Think of it as division.
Okay, good. The operation is division. And what's my goal? My goal for an equation is always to get x by itself. So then what I always say to a student is, why is x not by itself? The stupid 6. What's the operation? Division. How do you kill it? Multiply. Right? So this is the thought process you could have as a student. You can just do this with yourself, right? So yeah, you multiply both sides by 6, it's crazy. And you get x equals 18, it's crazy. And then 18 divided by 6 is 3, yay. So you guys do the back. I'll finally shut the hell up. You guys do the back. Yeah, work by yourself for a little bit, and then I'm going to kind of group you up, because some of the last ones might get a little tricky. I didn't put any inequalities on here for some reason. Oh well, too bad for me. All right, guys. I think the first few hopefully were good. Yes. I said to check your solution, but I mean, if you plug a 4 in, 4 minus 7 is -3. Not too bad. This one trips some people out, but what did you guys do for this one? Anybody?
I canceled.
Yeah. The x is not by itself because something is adding to it, so I'm going to subtract that thing from it. Oops. So they cancel and I get x equals 0. And if I check it, square root of 5 plus 0 equals square root of 5. Check. This one, of course, you just divide. Is that cool? This one you just multiply. And so you get 21. Then you can do 21 divided by 7 is 3, and that checks. Alright, so those are pretty basic. Then I step it up just a little bit. First step on this one is to add 1. Now I could divide by 4, but if I divide by 4, I'd have to divide each thing by 4 and make all these fractions. Screw that. I'm going to add 1. And then so you almost always divide last if you're going to divide. So you don't make fractions too early. If I get a fraction at the end, I'm so cool with that because I'm done. What about this guy? Good. Subtract 6. And divide by -5 because that's the thing that's multiplying my x dude. -1, is that cool? I think I saw most everybody getting these doing fine. It's a little trippy down here and definitely here. So this one, I've got everything on both sides, so I just pick a side. So what did you guys do to get your x's together? Subtracted. Okay, subtract 4, sure.
And then subtract -8.
Subtract 8, sure. Find my -5, so I get x is 3. Now you could have also subtracted 3x, added 11, right? In case you can force no negatives to show up on your x. So you don't make a negative mistake later, but it doesn't matter. Either way you do, you're gonna get the same answer. Okay, all very exciting. Here's my first layer of, what do you do here? Yeah, just distribute. If I distribute, then everything's free to move around. Here I can put those together, and then what? Yeah, subtract x, subtract 1. Ciao. And if I check my answer, x is 2. 2 plus 1 is 3 times 2 is 6 minus 1 is 5. 2 plus 3 is 5. 5 equals 5. Yay. All right, now, I went a little fast there, I'm sorry. What about I? Did anybody try I? Did everybody try I? All right, I know you guys. Be quiet. You may not get a chance to try I yet. Okay. So what's the first step on I?
Distribute.
Yeah. So there's two main places students can make mistakes. Here, I'm going to make a mistake. Okay, I made a mistake. What mistake did I make?
The six.
Yeah, what am I distributing? -2. So this should be a -6. Okay, so that's the first kind of level of mistakes students can make, is not to bring the whole number. It's a -2 output. I gotta bring that negative through. So now I can combine stuff. 11 minus 6 is 5. And of course, -2x plus x is -x. If I subtract 5, I get to this weird place. Are all my x's together? How do I get my x's together?
You don't have to.
Hmm?
I think at this point you don't have to because it just.
Yeah, it depends. You can either realize what this means. What did you say this means?
X is X. So it's any real number.
Yes, all real numbers. But most teachers want you to get to the point where you have numbers, like it's easy to tell that 0 equals 0. So here's the thing. Whenever you solve an equation, here's how you interpret it. When this statement is true, then this statement is true. Let me say that again. When this statement is true, then this statement is true. So most equations have a singular place that makes them true. So if I interpret this the same way, when this statement is true, then this statement is true. Is this statement ever not true? It's always true, even on Wednesdays. So this will be all, it doesn't matter what number I put in. So if the x is, now what's really funny to me is students hate that there are letters in their math. But then they get this problem and they try to save the x. Somehow the x is left alive at the end. And I'm like, the x is dead. X is dead, Zed. It's dead, it's gone. So let it go away. If the x cancels, that must mean that our choice for x doesn't mean shit. It's either always true or it's always false. So if I would have gotten 0 equals 1, the answer would have been no change. There would have been no saving that poor dude. And real quick, what if I ask you this? Here's a really silly question. That's all we have. Is there any number that is one more than itself? Think of that just for a second. Is there any number that is one more than itself? That number is one more than itself. Is that possible? So if I set up an equation from that statement, that equation should have how many answers? Is there any number that is one more than itself? I love you guys. Is there any number that if you add 1 to it, you get the same number? Ain't no way that's happening, yes? If I add 1 to anything, it's 1 bigger than it used to be, yeah? So if I set up an equation that represents that statement, that better have no answer, correct? So what the shit does that look like? I don't know. So I'm saying, I need real clear. Is there a number that is one more than itself? That is what that looks like mathematically. A number is one more than itself. How do I solve that? Are my x's together? How do I get my x's together? And this is where students, it's really funny to watch. A student will desperately try to save that x. Let it die, it's dead. 0 equals 1. How do I interpret when I'm done with the solving an equation? When that statement is true, then the original statement is true. Is 0 ever equal to 1? No. So is the original equation ever true? Nope. So no solution. Exactly what we expect from such a nonsense statement. So any equation I write down, it could have all real numbers. It could have an infinite number of solutions. It could have 0 solutions, or it could have 1 solution. Most of them have 1 solution. These linear ones. Okay. All right. I think that's enough for today. Did everybody get a practice final? Did everybody get a final study guide?
I did.
So we're going to start our review for final this Thursday.
Finals next Tuesday?
Finals next Thursday.
Next Thursday.
Yeah. So we have 2 days of review.
Okay.